Hi guys, how are you doing? So I'm really happy to be here today in Moscow to talk about how we can build effective approximate searching and spell checking techniques. First, I'll give my quick introduction about myself. So my name is Ling. I did my undergraduate at New York University, focusing on natural language processing, particularly in multilingual and phonetic techniques. So that's the talk today. We're talking about phonetic approaches to spell checking using sounds instead of letters. And I did some internships at Facebook, Palantir in the US. And now I'm living in London, I'm one of the first engineers at an AI startup called Aiden.ai, and we are building a virtual marketing assistant. So someone who sits on an AI that sits with you on Slack, and you can ask it questions about, how are my advertising campaigns in France and Russia doing this week? How is that compared to last month? Hey, can you monitor these campaigns for me and tell me if something's happening? Can you predict for me what's going to happen next week? So we're building this AI that's interface is 100% natural chat. So we're working with a lot of interesting machine learning, natural language processing, and data science problems. So one interesting problem is fuzzy search. And another way to title this talk would be, can we build an awesome searcher in just 30 lines of Python? Hopefully we'll see how far we can get along this. So the core problem we're dealing with is spelling is really, really difficult. No one can spell. Even it doesn't matter who you are, like how educated you are. Anything where you have a text box, your users are going to make a lot of mistakes. And let's try and kind of understand why is it important why are these spelling errors really fatal for engineers and product designers? And the central idea is spelling something wrong will lead to product failure. It's going to break your product. I think all of us have had the experience where your friend's trying to meet you at a restaurant, and you're trying to type the name of a restaurant into Google Maps or Yelp, and you just spell it a little bit wrong. Especially these days, if you go to like San Francisco, they all have kind of hipster spellings. They spell like coffee with a K or something like this, and you know what it's called, but you type it and it's just slightly off. Or you have a friend you met at a conference, or at a bar, you met someone like Natalia or Natalie or something along these lines, and you're trying to find them on Facebook, and you try typing it 3, 4, 5 different ways until you find it, or you might not find it at all. So, the same thing of Google Maps. I was looking at Google Maps here in Russia, and some of the shops were spelled with Roman letters, and some of them were spelled with Cyrillic letters. So if you don't have a good technique to handle this, if using the wrong alphabet, the user's not going to be able to find the entity they want. So for a lot of these content-driven apps, like Spotify for music, Google Maps for locations, YouTube, Facebook, anything where you're driving of content, your user has to first search, and if you don't have the right search, your whole product is going to fail. And beyond this, if you're doing any natural language processing or doing any machine learning, what you'll find is for example, if we're working at Facebook and we want to do sentiment detection, we want to say, is this post happy or is it sad? And we'll make this model with this nice data from universities, and do this training, everything works great. Then when we deploy this to the real world, we might find that actually our model was completely messing up, and we look into it and say, why is everything breaking so much in production? And it turns out users are spelling badly, and we haven't trained our model for this at all. So the same thing for any kind of machine learning application dealing with text, like Alejandro's example right there. If you wanted the user to start writing a story and then the machine finishes it, you actually have to first spell check that data. And the same thing if you have a speech recognition application, maybe you're building a driving application and you have a few commands via voice, like navigate to or take me home. And then the speech recognition, we're using Google's API or IBM API. If it comes back slightly wrong, and instead of saying take me home, it's take home. Actually, we might be able to treat this as a search problem and treat it, instead of the speech recognition mistake, treat it as a spelling mistake and see if we can recover into a correct result. So I'm going to take an example for this talk, and it comes from a Google data set that we released many years ago, maybe 10 years ago. They released a data set of all the ways people spell Britney Spears. So, how many ways do we think people spell Britney Spears? When I asked this question, I think maybe 20, 30, 40 ways. I mean, if you try to imagine it, you probably can't imagine more than 15 ways, 20 ways to spell Britney Spears. But actually, when Google released a data set, they showed that people spelled Britney Spears in 593 different ways. And it's not that difficult of a name, I think. And it's really, really fun because this data set not only tells us all the ways they spelled it, it tells us also how often they happened. This is only the ones that Google caught. So Google has probably one of the best spell checkers in the world, but there might actually be other ways people tried spelling it that Google didn't catch and couldn't recognize. So let's take a look at the errors. So I decided to plot the errors. I said for each variation of spelling, how much percentage does it make of all queries? So you can see right near the top, we have this really high bar. That's about 75%, the first data point. So 75% of queries were just correct. That's fine. And then we have this huge long tail of over about 600 ways to spell Britney Spears. And at the bottom, we're looking at the last ways to spell it only happen 0.001% of the time. So you can see, basically, there's a few ways that are kind of common, and then there's a huge long tail of errors. So this is a problem that makes spelling really hard. And you see, in this example, 23% of queries were spelled wrong. So if this was my app, that means every time my app is used 4 times, one of those times is going to make a product failure. So this is why kind of spell check has to be, we don't think about it first when we're building our product, but really to get a good user experience, we need to treat it as a first-class citizen. And so look, if we look into that, flip that around and say, let's look at it as a cumulative distribution. How many variations of spelling do we have to capture to get a certain % of error correction, or to recover from a certain percentage of errors? So you can see here, this is kind of, if we want to capture 90% of errors, we have to recognize the top 18 ways to spell Britney Spears. If we want to capture 95% of errors, we have to recognize the top 40 ways. If we want to capture 99, that goes up to 196. So you see, to go from 90 to 95, 5 points, we need only 22 more variations. To go from 95 to 99, 4 more points, we need 154. And then just to go up 0.9 points more, we're going to need about 300 more. So there's like a very, very rough rule of thumb is that if you want to increase your accuracy just by 10%, you're going to need to recognize 10 times more. So every 1.1 times the performance will take double the effort. 10 times the effort. Let's set a goal. Can we develop an algorithm in 30 lines of Python that can correct the error 95% of the time? So here are the top spellings of Britney Spears, just so to get a feel for this problem. Number 1, it's spelled correct. Nothing wrong with it. Number 2, it's very close. They added an A before the N and took out the E and added a second T. So it's Brittany instead of Britney. But basically, small error. The next one is actually very close as well. There's an extra T. So this is actually, I think, a correct way to spell Britney. People spell the names in different ways. So this is what's really difficult, Same one, number 4 is the same as number 2. Number 5 is they just missed the E. So you can see here they're actually very similar. And this is kind of one of those problems that's interesting because as a human, I look at all of these and straight away I know exactly what the user meant. But as an algorithm, it's very hard to specify exactly what these errors are and how to convert them to the true phase. So there's a really famous spell corrector made by Peter Norvig. Peter Norvig is quite famous. He's one of the research directors at Google. And he wrote the book, AI, A Modern Approach. And he also was the director of search quality at Google. So he really knows about search and Google spell corrector. And he has a very famous and old blog post where he says, hey, people often ask me how to build a spelling corrector. And so I'm going to show you on 1 page of Python code. And his story goes, he was on a plane and he did some part of this on a plane. And actually, basically the whole thing boils down to one concept, which is the Levenshtein distance. So let's look at Levenshtein. Levenstein is basically a distance metric. A lot of us would have learned this in school, but it's to say how similar is one string to another string. And it says, okay, let's define 3 types of errors. Insertions, where we add a character that's not supposed to be there. Deletions, where we're missing a character that's supposed to be there. Or substitutions, where one character has become a different character. So if we look at the 2 strings, elu, E-L-L-L-U, and hello, the distance will be 3, because here we've the H has been dropped. We've added an extra L, and then we've changed our O for a U. So here you can see it's a very simple metric. We just basically say what's the quickest way to get from one string to another. If you look at Peter Norvig's, basically he's saying, I'm going to use that distance and make all the variations. So I'm going to take the letter X and add it to every position. I'm going to take every letter and try delete it. I'm going to basically try generate all the variations I can and see if any of these turn into real words. So basically, this is a simplified version of his code. First thing we do, we take the word, look it up in the dictionary. If the word's already there, it's correct. We don't do anything. Then if it's wrong, we take all that word and generate all variations that are one distance apart. So do all the insertions, all the deletions, all the substitutions. Then we look up all these words in the dictionary. If one of those is right, we're done. If it's not right, we take all the variations and generate all the variations of those variations. So this is an exponential technique. You can see you're doing some kind of cross multiplication. And then if any of those are correct, we look it up in the dictionary and we're done. And sometimes, if you generate a lot of variations, maybe more than one of these is a real word, so you have to score them. You have to say, out of these words, which one is most likely? And he doesn't say how to do this, but you can use stuff like statistical techniques. So you can say, like, if you have the word, the cat sat on the, and then there's MA, it can either be the cat sat on the map or the cat sat on the mat. But then you can use statistical counting, so you can count from ebooks, count from Wikipedia, count from the internet, and the cat sat on the mat occurs much more regularly in English language than the cat sat on the map. And we can use these kind of techniques to score. So that's essentially his spelling algorithm, which is a very, very simplified version of what he said happens at Google. And if we apply these to the top Britney Spears errors, we can see actually the distance is only is 1 or 2 for most of the cases, except the second case where it's 3. So it actually, on this data set, just this simple approach caught 94% of queries, or in other words, that's 70% of all misspelled words it was able to correct. So it's very simple, fits on one page, and is not bad actually. But let's think about the 70% number a little bit. So in spelling correction and fuzzy search, we're basically searching through a world of possibilities. And so we're balancing 2 things. We're balancing accuracy and speed. If you want to go slower, you become more accurate. And if you want to go faster, you become less accurate. So you can see this. If you don't do any edits, you only generate 1 variation of your spelling. You don't correct any errors, and you'll have less than 1 millisecond search time, because it's basically instant. If you generate one distance away, you're going to generate 800 spelling variations. You're going to be able to correct only 54% of errors, and you're still going to be very, very fast, 1.4 milliseconds for the slowest query. If you generate 2 away, you're going to look at 600,000 variants. And you're going to correct 70% of errors, which is what we just saw. And actually, this is wrong. It's not 320. It's 640 milliseconds. So you're actually almost 1 second per word to search. And then if you go one more distance, if you try to generate, again, the variations, you're going to get 57 million different ways of spelling Britney Spears. Actually, I wasn't able to benchmark how accurate this is because it takes too long to run. A single word will take 6.5 minutes to search for. And the question is, okay, if we, so this technique, you can see it's okay today. It gets 70% of errors, but it can't get any more because after any more, it will become too slow. And the problem is 70% might not be high enough for you. You're still losing maybe 1 in 20 words. And if we have, for example, a 200-word Facebook post we're trying to spell check, that might take 7 seconds to spell check. And the other question is, I said that to get 95% accuracy, we just have to find 40 ways to spell the word. Right here, we're generating 600,000 ways, and we're still not finding those 40 ways. So basically, is there a smarter way we can do this to get from 70% to 95% accuracy? And can we make it faster at the same time? So let's look at the same top 10 mistakes again and see in terms of sounds, how do they sound? The first one, Brittany, they added an A sound. Second one, Brittany, it's completely right. There's nothing wrong with it. It's actually a fine word. Next one, Brittany, again, they just added this sound A before the N. That's not supposed to be there. Then Brittany, that one's again, it's correct. And what we notice here is most spelling mistakes either actually sound correct if you try say them, or they are only one sound apart from a true sound. So whereas with a Levenshtein distance, essentially what we're doing is we're saying, oh, I'm typing the word Brittany, and my finger slipped, and I hit a random character on the keyboard at a random point in time. But if we look at the spelling errors, that's not what happens. Most spelling errors are not because people hit the wrong key on the keyboard. Most of them are because they just spelled it wrong. They have the sound correct in their head, but when they try to type it, they just use the wrong letters. And especially in English, you know, the same sound can have many ways to write it. And that's where a lot of this problem comes from. So if we look at this from a phonetic point of view, the errors are not random. They deal with sounds. And instead of modeling the word or the string as a series of characters, we can model it as a series of consonants and a series of vowels. And we can use the same techniques that Peter Norvig described, do deletions, insertions, and substitutions, but instead of on characters, doing this at the sound level. And actually, one of the advantages is we can quantify distance better, because in the Peter Norvig example, we're saying, I know, my finger's gonna slip and I'm gonna hit a random character. Instead of saying that, actually, I know that maybe I know vowels, for example, are more easy to add or forget than consonants. And I know some sounds are closer to other sounds, like s and sh are very close sounds. B and p are close together. But no one is going to confuse sh and p. They're too different. So we have more fine-grained control in this approach. So here's the whole thing. Here's how we do fuzzy search. Basically, we say, I'm getting a word, a query term, and I have a dictionary of possible words that I actually recognize. I want to get 10 results, and the distance is basically how much variations I want to generate. So I basically say, okay, I'm going to turn my word into sounds, and then however much times I want to do the variation, I say, look up my word. Is it in the dictionary? If it is, add it to my results. And then I generate new variations. And then that's it, basically. Then I go back and do it again. I look up all the variations of a dictionary, and for each of those, I generate new variations. So basically, there's only two aspects here that we need to understand how to do. How do we turn our string into sounds, which is phoneticization? And how do we take those sounds and then generate all other sounds that are similar to that, which is candidate generation? So first one, phoneticization. So there is an alphabet called the International Phonetic Alphabet. You might know this when you're learning a foreign language. It's a set of symbols that uniquely describe how to what something sounds like. So it's perfect. One letter is one sound, and it's across all languages. So actually, between English and Russian and Arabic, there will be some set of these of the exact same sound. And the idea is if you can learn the phonetic alphabet, you can read every language. And this is really nice. So if we look at the word hello, it's spelled like this in the phonetic alphabet. H, this upside down E, which is a, and then the two L's became just one L sound, L, and then the O became a U sound, hello. And then each character is called a phone. So a phone is just one sound in the phonetic alphabet. And English is a really tough language. So how do we actually understand how to change from a string to sounds? One approach is we can use what Alejandro showed. We can use deep learning. You can use deep learning or machine learning for almost anything, and I have tried this. It's okay. It works fine. The problem is it's too slow. If we're building a spell checker, we need it to be very, very fast, and we don't have time to run a neural network every time a word comes in. So what we can do is we can do a simple the simplest thing possible. Sometimes in programming, when you're dealing with a difficult problem, it's always let's try the dumbest, simplest idea first, which is let's do a mapping. These letters become this sound. And actually on Wikipedia, you can find mappings for every language used by people who study language. And there's also dictionaries where it will tell you for every word how to say this word. So Oxford has one, Cambridge has one, but actually CMU University in the US has an open source one called CMU Dictionary. And so actually, this is, to make a note, is that this is quite difficult in English, but for some languages like Spanish or Arabic, it's very, very easy. Those languages have very straightforward. The alphabet is almost exactly the sounds already. So if we just go to Wikipedia and we say help IPA English, here we go. We're going to get this page that's going to show you all the sounds of an English language and different ways you can spell that sound. So you can see here, there's the sound j, and you can spell it with a G in giant, with D in badge, and with a J in jam. So there's 3 different ways to spell the exact same sound. And the really nice thing about Wikipedia is in every language. So if you take that URL and change English to Russian, we get the exact same thing in Russian. So, and it's the same alphabet on the left-hand side, so you can do this for any number of languages you want. Just look it up on Wikipedia. And so I did this. I tried to make a mapping as a simple JSON file, and it took me 15 minutes, and I have my mapping. Really simple. The letters on the left, like THE, become the sound the. So B becomes B, D becomes D, G becomes either G, J, or J. So straight away you can see English is very fun as language, because if you look at the right-hand side here, all of these are just semi-vowels. And they're just, this is why it's really hard to pronounce words correctly, because there's a lot of special rules. When you combine these groups of letters, they form a new sound that doesn't really make sense. And that's because English is kind of historically a very mixed language. So they have these rules from all these different languages. But some languages are more straightforward. But this one is not complete, but it's a okay mapping for English in only 70 lines. So let's take this and see how well it works. So I can turn basically strings to sounds in 40 lines of Python. First, what I do is I take my word hello and I tokenize it. I put an underscore in front of it just to say this is an alphabet word and not a phonetic word, because actually some characters like B and H are the same in both, so I want to not get confused. And then I turn it into sounds, so I turn all the underscores into $ to know that, okay, now it's been turned into a sound. And lastly, I just remove repeating sounds, because and when you're dealing with sounds, you can't have repetitions, because if you have 2 A's, it's just a really long A. It doesn't make sense. So we lastly remove repetitions. So to make the sounds, basically what I say is I get my mapping, and I just run through my mapping every time. So for with my word, for every rule, I try apply this rule to this word and see if anything comes out. And I just do this over and over and over again. And actually, because we saw the rules sometimes produce more than one sound, it can happen that one word might have multiple ways to say it. So that's all I do. I just run it in a loop and just apply the rules over and over until there's no more rules to apply, and then I'm finished. So here, if we look at the word hello in the phoneticizer, it came out correctly. If we look at the word, trying to phoneticize the word China, it actually gave 2 examples. One is correct on the left. That's the word on the left is China. On the right-hand side, it says Kahina, which is not correct. But actually, it doesn't matter, because at least the correct one is in there. And here, the word Moscow came out correct as well. And so we're being approximate, because this is fuzzy search after all. So it doesn't matter that we make some mistakes. And actually, with the simple technique of mapping, we can actually get we can find the correct pronunciation most of the time. So that's it. That's how you turn a word into sounds. And now we have to say, given a sound, how can we go to all the other sounds that are similar to that word, which is called candidate generation. So here I have an example. If you have a word hello, I could add a sound, become hello, could become hellos. I could delete a sound, so hello could become allo. Or I could substitute a sound, so hello could become hallo. So these are the exact same idea as Peter Norvig's, except now all of these have a score. We can say, okay, how likely is it for an E to become an A sound? And we can say it's quite likely, so this has a low cost. So let's quantify this. To quantify this, basically every sound is made up of a list of features. And these features are things like, do you use your lips for the sound? So the sound b and p, you use your lips for, but the sound s, you don't use your lips for. So that's one feature. Does the sound come from the back of your throat or the middle of your throat? And there's a list of about 20 features, and basically we can use this vector to say, okay, these two sounds are mathematically similar because they share a lot of properties. And I've actually helped you guys out here. So I made an open source phoneticizing library. It's called Python. You can just import it, and you can say, OK, tell me the distance between these two sounds. So the first one on the left, on the top, A and I, distance is 0.1. They're pretty similar, A and I. B and P, B and P, very similar, 0.04. But D and T, same thing, 0.04. They're very similar in your mouth. But you take sounds like B and S, very different. The distance becomes 0.47. And then distance of N and A, completely different. Distance is 1. So straight away here, it basically does what I explained before, which is looks at these vectors and just says how many are different. I just took that table and I made it into Python, a Python file basically, and it just says, for this letter C, here are features like feature 0, syllabic. Is it a vowel or not a vowel? It's false. And it's just a big array of false, true, and none. And then I just compare them very simply. Here's a code that calculates a distance. Special handling for spaces, and then you check is it a vowel or is it not a vowel? You get the vectors here, and then basically for all the vectors you just add up. If it's not different, you increase the score, and straight away it's a very, very simple technique to see how similar two sounds are. And they're weighted, so some features are more important than other features. And we can do the exact same thing as Peter Norvig's algorithm. We generate deletions, generate insertions, generate substitutions, and see if we can find a word in a dictionary. And we tried this, and it does work. It works pretty well. But the problem is it is still really, really slow. It's something you'd want to do in research, not something you want to do in production. The problem is because these things are now ranked, so we said some substitutions are cheaper than other substitutions. In Peter Norvig's example, everything was the same. But because our ones are ranked, we have to maintain a sorted list. And maintaining a sorted list of 360,000 items is really expensive. It's a heap, but it's a very, very expensive operation. And so you basically, the idea is good, but we need to improve it to make it fast enough. So what can we do to reduce the complexity to make it faster? What we can say is that actually, if you look at the sounds in the world, some of them fall into these natural categories, like B and P are almost the same sounds. D and T are almost the same sounds. And within these sound groups or these sound clusters, we can easily move from one sound to the other by accident. But there are some sounds like B and S, which we would never move from. So let's just say we're going to stay inside our groups. We can move inside a group, but we can't move between groups. And we're going to collapse these. So we're going to say instead of having, English has about 50 sounds. Instead of having 50 sounds, let's make it something like 20 sounds. And the advantage of this is if we have these clusters, we have less insertions, less deletions, and actually we completely remove substitutions because substitutions can only happen within a group. So to be more concrete, we have to take the world of all our sounds and cluster them together. And the really great thing about Python is everything is easy in Python. Python is great and productive. So you can cluster any data in 20 lines of code. So I just import SciPy, and I calculate the distance matrix from every sound to every other sound, and I just throw it into NumPy and say, cluster this. And then it comes back and says, OK, I clustered it for you. So here we have turned our sounds into groups. You can see here like A and AR became one group, I and EI become one group, V and F become a group in 15, B and P became a group, and it's really great. It's almost like machine learning, but really simple and fast, almost like magic. So basically what we're saying is instead of using the letters B and P, let's just represent this as number 16. And this is an idea that's a very old idea. It comes from the idea of SoundX, which is used by the United States Census and was developed almost 199 years ago. And basically it's saying, let's take these groups of letters and use them a number to represent them. So basically, we added one last step. We turn our hello to these numbers, 19, 1, 18, 3. So we lose some distinction, but in exchange, we become a much, much faster algorithm. So now our candidate generation is much simpler. We don't have substitutions, and we have deletions and insertions, but on a smaller set. So this is the whole algorithm running. We tokenize a word, we turn it into sounds, we strip away the repeats, we cluster the sounds into categories, and then we just go in loops trying to generate variations by adding or removing a random number. So you add number 2 and add number 3. Number 3 might be certain sound category. We just add that category or delete a category. And every time we do this, we look up a word in the dictionary, and if it's a word, we return it as one of the results. So that's it. That's the whole search algorithm in only 30 lines of Python. And plus the Python library, which will, if you import it, it will handle clustering or handle phoneticization and that kind of all the sound stuff for you. And then the actual search problem becomes just 30 lines of code. So how well does it work? I benchmarked it again on the same data set. We went from 70% accuracy to 95% accuracy. So we improved about 34% of our 34% more errors were corrected under this phonetic approach. And the query time went down from 33 milliseconds to 25 milliseconds. So we're looking at a 25% speed improvement. And the worst case query time, which is the time it takes for the longest example, went from 670 milliseconds to 300 milliseconds. So the worst case reduced by half. And with correcting 95% of errors, that means in absolute terms, over 99% of things a user types, you'll be able to recognize. So that's a lot higher than 75% with no spelling correction at all. So finally, it's very important to understand that this technique to spell correct using sound is meant to be combined with other techniques. It's not meant to replace your databases or your Elasticsearch. It's really a tool to make everything else work better. So you can do this with Peter Norvik's algorithm. This technique doesn't handle very well when you accidentally press a button wrong. So you could do both of the spell checkers side by side. Or you could use this one to generate the top 10 results, and then use Levenshtein distance to rank the results, for example. Same thing if you have Elasticsearch or IndexedDB, some kind of like index database, MySQL, Postgres, you can store somewhere all your tokens, spell check onto that list of tokens. Your tokens might be names of restaurants or names of places. Spell check first and then do your search second. We can also, you have a very powerful thing, which is we can go across languages. So because everything is indexed by the sound, we can, for example, take a restaurant and its name could be in Russian or its name could be in English, and then the user can search using Russian alphabet or English alphabet, and they're going to map onto sounds at the end of the day, so they search very quickly. So you can cross language barriers very, very well. And this is really great if you're running something like an e-commerce site, because you can really improve your hit rate and generate more revenue. Same thing, if we have NLP or speech recognition, we can kind of find out what did the user, if a random word comes in through speech recognition, we might say, okay, did they mean something else? So a good example is if you're having a phone dialer and you say call Julie, and you don't have a Julie in your contact list, you can say, oh, there's another contact called Jules, which is very similar in sound, so let's just match these two together. So in recap, basically what we learned is that people are very bad at spelling. Mistakes. So this is a fact of life, and actually it's very tempting to say my app is not broken or my product is not broken. It's the user that's broken. But really, I mean, we're dealing with real people. Real humans use our products, and they make mistakes. So for us, our product to work for them, we need to take responsibility for dealing with these spelling mistakes. So spelling mistakes are our problem. They break our products, so we need to fix them. And there's very many variations on how to spell something, but the key is these differences are not random. They're mostly mistakes that are driven by having the wrong sound. Most of them are dealing with just one sound away or two sounds away. And it's very powerful because of how productive Python is to build a very powerful spelling corrector or fuzzy searcher in only a few lines of code. And importantly, this is something that is designed to be used within our existing tech stack. It's meant to be, you have a component that's working, but we want it to work a little bit better. So we can combine it with all sorts of NLP, Elasticsearch, database searches, and it can make everything else better, but not really as something to be used on its own. And you can also cross language barriers. And so there's a few caveats in that. In this talk, I only gave examples of how it performed on one data set. The reason I didn't explain in general how performance works is because it really, really depends on your situation. If you have a small vocabulary you're dealing with, it's going to work really well. If you have a huge vocabulary, it's not going to work so well. And it depends on how you combine it with other tools. So really, it's not something that you can just say it works like this. It's something that in context can improve everything else. So I just took the most simple example, which is one search term, and did a benchmark on that. But the actual performance is much more nuanced. You have to really think about how it works in the context of everything else. So all the code from today is online on GitHub. You can check it out. There's Python, which is a phonetic library, and then Fast Fuzzy Search, which uses a phonetic library. So it's all open source on GitHub under the MIT license. So give it a go, play with it, pull requests, let me know what you think. And that's it. So it's time for questions. And if you have any questions, let me know. Give me an email.
And applause. Thank you. That was amazing. Phonetic distance is the thing. And now, коллеги, у нас есть 10 минут, очень хороший тайминг, чтобы позадавать всякие разные интересные вопросы. Прошу, кто хочет поинтересоваться. Сейчас, когда спикеру некуда бежать, когда он не может скрыться за чашкой кофе. Рита.
Thank you very much for your talk. And what are your ideas on spell checking slang words or probably new words that are not yet in the language? What approach would you use for this case? Thank you.
Yeah, it's very good, actually. So I had a professor in university who said that actually language, the written language, is made up. It's something that's fake. So actually, if you look at history, all people had spoken language, and sometimes they get colonized by the British or something, and then the British add a writing on top of a language. And slang is actually a form of this. So a lot of slang, like thanks, THX, is actually just people expressing their sounds, but making it with their own rules. So one nice thing is some slang, which sounds like a real word, might automatically get recognized. But there's also the other kind of slang where people make up new rules. And I think with this, it's Google has a very interesting approach. At Google, they say everything we do at scale. We do it for everyone in all languages around the world. So this is the only way to do things at scale automatically is to use data. So basically, one example I would have for this is if I'm looking for new words that don't exist, I could take, for example, a corpus, like all the posts on Reddit. So a really huge corpus of like 1 billion words, and I count how often each word happens. I do spell correction, but there's going to be some words in that which don't match onto any word in my dictionary. So for those words, I'm just going to say, this is a new word. I'm going to consider this, or the most likely way to spell this word, as the correct spelling, and just learn that above this threshold, all of these are words. So, look at your data, basically.
Рита, там.
When you mentioned the technique you've developed doesn't work so well on large vocabularies, is that because of accuracy, or is that just the performance because it has to generate so many permutations?
It's not because of performance, it's because when you have a large vocabulary, in language, words naturally, there's a lot of words that sound similar to each other. So if you have, for example, French and English, an app that works in both language, and you have chocolate and chocolat, it's like, which one are you matching towards? And what the idea here is, to solve this problem, you have to combine it with other tools. You have to say, okay, I'm going to look up the user's history and say they've always searched for English things, so I think they mean the English one. You have to use context to disambiguate and to rank the results. So this is really great to surface the top 10 results, but then you have to decide out of those top 10, which one do you pick?
Thank you.
Коллеги, Кто еще хочет позадавать каверзные вопросы? Рита.
I'm a huge Aiden fan.
Oh, really?
Yeah. Can you tell a little bit more about what are you using in Aiden? So you are using this fuzzy character and other stuff, yeah.
Sure. So at Aiden, one of our central problems is a caveat is that this character actually doesn't come from Aiden specifically. It might be something we incorporate into Aiden, but it comes from my research work at university. But at Aiden, in general, the key problem is we're a bot that lives on Slack. So you just talk to it like you would talk to a person. And when we talk to people, again, it's about user experience. We talk to people in a natural way. So that means we make spelling mistakes and we have things in a very vague way. So when we started Aiden, if we said, if I wanted to ask for, hey, what's my cost per install in Canada? And instead, I typed, what is my cost per installs in Canada? It would completely break out NLP. It just wouldn't work. So we have to add this very small layer of spelling correction. And actually, as soon as we did that, our accuracy rose by a lot. So really, it's a pre-processing step before we do intent detection and entity extraction. And it really improves our techniques.
And you're using TensorFlow or?
In Aiden? In Aiden, we're using we're using not TensorFlow right now, but we have a language model, and we're at a stage where we're kind of improving it, and so we're expanding into new techniques. So actually, one of the things we're looking at right now is TensorFlow.
Thank you.
Коллеги, еще вопросы? У нас есть целых 4 минуты. 4 минуты раз, 4 минуты два. Рита, прошу.
Thank you for your talks. I have a question about your talk about Russian language and English. What about some kind of where tone is have meaning? It's like Chinese language or Thai language, where it have different tones, and I guess this algorithm will not work too much well like with European languages.
Right. Yeah. So what about with so there are some like symbolic languages like Chinese. The alphabet size is over 50,000. So if you try to Levenstein on this, it will not work at all. It will be like a huge number of explosions. So with the one thing to recognize here is in symbolic languages, you almost never miss a symbol completely, because if you're typing on a keyboard, it takes 3 or 4 keystrokes to enter a symbol, so it's not going to happen. And it's the same idea, basically. Sometimes I'm typing really quickly and I'll accidentally enter the wrong symbol, but not notice it and carry on. So we can use the same ideas. If I hit 3 keys and one of them is wrong, or maybe I'm kind of thinking strangely and I can't, I just pick the wrong symbol, I can say what are symbols that sound close to the symbol and see if they make more sense in context. And actually, this is a really good thing that Google Docs does. So sometimes you're typing on Google Docs or Microsoft Word, and you type a word that is correct, but it still gets the red underline, even though it's a real word, because Google or Microsoft thinks, hey, you actually meant a different word, because in context, this word is strange. So really, it's driven by context, using a language model, counting statistics, and saying, statistically, this doesn't look right in this position.
30 seconds, I will do a small translation because it's a kind of complex topic. Вопрос был, а что делать с японским, китайским и прочими иероглифами? И спикер ответил совершенно правильно, что японцы, китайцы и прочие иероглифисты, они не вбивают с клавиатуры иероглифы. Они вбивают латинские символы, и затем специальная программа предлагает им там один из 20 иероглифов, который этим символам соответствует. И поэтому, если мы хотим сделать спелчекер, который будет работать с иероглифами, то нужно работать не с самими иероглифами, а с вариантами латинского символа. То есть программа смотрит, что человек мог ввести, чтобы ему предложили набор символов, в котором он кликнул не на тот символ. Вот такой вот забавный обратный реверс при спеллчекинге. Коллеги, последний вопрос. Давайте спасем спикера, иначе последний вопрос задам я. Это будет страшно. Кто готов спасти спикера? О, Рита. Okay, last question.
Okay, thank you. What you can say about grammar rules in English, like irregular verbs or something like that?
Yeah, so this is it's interesting. It's basically, yeah, I think for grammar rules, it's same thing. It's about driving with context. So if, for example, I like to swim, and you instead of the user types I like to swam, if you do a search on swam, you'll also get the word swim because they're very similar words. And then you use, again, context. You use statistics. So you say, how often in Wikipedia do I see I like to swim? And how often do I see I like to swam? And I like to swim happens much more, so I'm going to correct it, even though it's a real word. So in grammar, we can kind of say, let's forget about encoding the rules and just use statistics to figure it out.
Okay, thank you.
Thank you. So please, applause. Ding.